All right, so today we'll talk optimization, just unidimensional. Just optimization of one dimension, okay, that's all. So basically, the idea is simple, right? You've got some kind of function, right? And all you want to do is optimization. All this is just, this just translates to finding local minima or maxima. That's all it is. So in this case, we would say, all right, just, what is this, right? What is this location? Assuming that's the maximum. Is that the maximum? No, the maximum. I'm close, but right here? Is this it? I don't know. That's probably it. Okay, we want to know, what is this location? Okay, so what is the value of x that maximizes our function? Okay. All right. Now, why would we want to bother maximizing a function? What kind of function might we want to maximize that will be useful in the context of statistics? The likelihood function. Very good. All right. Exactly. So we have, you guys learned maximum likelihood estimation, right? This should be familiar, right? Maximum likelihood estimation. So how does MLE work? Thank you. No? Maximum. Okay, so all right. Well, maybe we'll just do a quick recap, right? Okay, so quick recap. Let's say your data comes from your data is coming from a binomial model, yeah? Okay, so like you're flipping coins, maybe, and you want to know, and either you get heads or tails, or you have some kind of random process that either produces a success or a failure, okay? So either it's part of category A or it's not, okay? So data comes from a binomial model. Let's say, so the data, our X is what, maybe 100 trials, and we have 64 successes. Okay, so maybe you flip the coin 100 times, you get 64 yeses, or you ask 100 people, are they going to vote yes on some proposition, and 64 say yes, or whatever. You got some random thing, you get 64 successes, right? So we want, and we're going to say each instance basically comes from a Bernoulli with parameter p, or we can say our vector x comes from what? Binomial with parameters 100 and p, right? So we have 100 trials and p. Okay, so what's the likelihood, what's the difference between a probability and a likelihood? Okay, well, maybe what's the difference between a probability density or mass function and a likelihood function? So, okay, so PDFs are for continuous probability distributions and mass functions are for discrete ones. So here we've got a binomial, so it's discrete, so you have a PMF instead of a PDF. But so the PMF, the defining thing is that the sum of all of your probabilities of X has to be 1, okay? And with a PDF, the integral of all of your probabilities has to also be equal to 1, right? And the PDF for the PMF is the probability of X, okay? And we are, and the PDF is defined by the parameters. The PMF for the PDF, these are defined by parameters. Okay, so these things, when we have Bernoulli P or binomial 100 and P, generally you'd have some kind of parameter there. This defines your probability mass function. Okay. The other hand, so the PMF for binomial with 100 comma P would be 100, choose X, P to the X, times 1 minus P to the what? I'm sorry, not an N, but 100 minus X, right? Okay, and so in our case, the difference here is that we could say, you know, what's the probability? So PMF typical use would be something like this: binomial 100, 0.7, and we ask, what is probability of 60? What was the number I said? 64? Okay, so we say, okay, if the probability of success is 0.7, the probability of getting 64 would be 100, choose 64, 0.7 to the 64, and 0.3 to the 36. That's good with everybody, right? Okay, so this would be your typical usage here. Okay, the likelihood function in this case, the data is given. So in the PMF, the parameters are given, and we ask what's the probability of getting something. Okay, parameter is given, or parameters are given. In the likelihood function, the data is given, and we calculate the probabilities as a function of the parameter. So this time we say, all right, we got n is equal to 100 and x is equal to 64. And so now we say, what is the probability of 64 given p? All right, so our function, our likelihood function, is a function of p. And this is effectively what it is, and we just say 100, choose 64, p raised to the 64 times 1 minus p raised to the 36. And we can vary p anywhere from 0 to 1, and so the likelihood function is continuous on the interval 0 to 1. And we're basically asking, what is the probability, or we would technically say, what is the likelihood of our data if I vary the values of p? probability or likelihood of observing the data that I have, if I vary the value of p. Okay, does that make sense? And in that case, we'd say, all right, well, I can calculate the probability of getting my data if I use p equal to 0.7, and if I do that, I would get, I don't know, let me just cheat, I would do d binom 100, Okay, all right. So I would just do like, what's the probability of getting 64 if I have 100 trials and my probability is 0.7, and that says, okay, this answer is 0.0362, right? And then we say, okay, well, what if my p wasn't 0.7, but rather it was 0.6? Okay? And it says, oh, the probability there is now 0.05914. Okay? And then we can say, all right, what if it was 0.5? Okay, well, then that's a lower probability. And we can just say, like, okay, what if I use 6.2? Okay, and 6.3 and 6.4, and we eventually we can kind of hunt around and we'd say, oh, you know what? The value of p that gives me the highest probability of data in this case was 0.64, right? And we would call this our maximum likelihood estimate. This is the estimated value of p that maximizes the likelihood of getting the data that I've observed. Okay. Is that recap of MLE okay? Yes. All right. What was that? Yeah. Okay. So what is the probability of observing the data that I have if I vary the value of p? We try out a bunch of this I just demoed, like the guess and check, like am I getting warmer or colder? Probably in 100B you had to you'd find this function and well, we can do this. All right. Okay, so we try different values of p, and we try different values of p, and we pick the value of p that gives us the highest likelihood. All right, and that is our MLE, maximum likelihood estimate. That's our maximum likelihood estimate. Okay. One thing about likelihood functions is that you integrate them, you're not going to get one. Okay, there's no requirement about the likelihood function needing to integrate to 1 or anything like that. Okay, PDFs and PMFs, you got to sum those up to 1, or they got to integrate to 1. Likelihood functions, it doesn't care. Right? We're just saying, what different values of p can I try out? All right, so if you had to solve this analytically, so we just plugged in a bunch of different values of p into R, and we said, oh, you know what? When I did 0.64, this is the biggest value I've seen so far, and we can do that. In our case, we can say, what do we have? We said the likelihood, a function of p, which is really just the probability of getting x equal to 64 for different values of p. Oh, I don't want to belabor this point. But, okay, and then, so probably in Stats 100B, you had to do this, I think, right? You had to solve this analytically. All right, and so how did you solve this analytically? Because we're trying to maximize this function, right? So we would, basically, you would find the derivative of our likelihood function. And you would set this equal to 0 and probably find solutions of p. Right? It turns out this is pretty hard to do, so you often deal with the log likelihood, right? So you don't have to deal with powers, and you would get you know, some constant times 64 p plus 36 times 1 minus p. And you, that's your, you know, whatever. Okay, log likelihood, you take the derivative of this and whatever. Okay, so anyway, this is what you did analytically, etc. And then you'd find, you know, your p hat is 64 over 100. Okay. Okay. You might encounter something where this is a tricky thing to do. So we have, so optimization methods are basically trying to solve this thing of maximizing a function, whether it's for maximum likelihood estimation, or you got some other reason to maximize or minimize a function. If you are training a model on you're doing like a machine learning thing and you're, quote, training the model, that often involves minimizing a loss function. Okay, a loss function being the difference between your estimations, your predictions, and the actual values. So, so for example, if we wanted to, we could do linear regression. And what does linear regression, the coefficients chosen for linear regression minimize what? The sum of squares, right? So you could come up with a function for the sum of squares. So another application is, you know, minimize the sum of squares of a function, right? Or yeah, minimize the sum of squares of basically, you know, the model. Okay. So anyway, these are just different applications of optimization. All right, and so let's actually look at one of the methods. All right, so the first one is basically all right, so we'll say optimization is basically equals root finding of the derivative. Okay, so this is kind of our first family of optimization methods. So on Monday we covered all these root finding methods. We said, all right, you got a function, let's find the 0, right? Let's find where the function equals 0. We just say, hey, you know what? If I'm able to find where the derivative equals 0, that's going to be a local minimum, a local maximum, maybe a saddle point. That's all we're going to do, right? So root finding is basically, you know, you've got root finding of some function f of x is find where f of x equals 0, right? All right, what we will have is we'll say g of x is, how do I say the antiderivative of f of x? Okay, and so basically, so that just means g prime of x is equal to f of x. And then so if we find roots of g prime of x, equal to f of x, basically equal to 0, right? Then we will have the critical points of g of x, okay? Which will either be local min, local max, or the saddle. That's pretty much it for this thing. Okay, so we'll do it for Newton's method. This is probably the Newton-Rapson method for optimization. Well, I mean, let's look at this, right? So, well, all right, just recall. Don't you love when teachers write that, right? So recall. But this should be like easy because it was Monday, right? So. But it's often like recall from like 7 years ago. All right, so Newton-Rapson for root finding was what? What did we do? Root finding of f of x, we would say x at n plus 1 is equal to x at time n minus, what did we do? F of x divided by f prime of x. Yeah? Okay, so let's do Newton-Rapson for optimizing g of x. All right, and we'll say let g prime of x equal f of x. Okay, basically, we can just use this exact thing, right? So we'll use the same exact thing, which is xn plus 1 is equal to xn minus f of x. Like, are we convinced that this will work? If g prime of x is equal to f of x, then this thing we'll find where f of x equals 0, which will be a critical point of g of x. Are we satisfied with that? Okay, and so if we want to just say this, then we just say xn plus 1 is going to be xn minus, and instead of writing f of x, I'm going to write g prime of x divided by g double prime of x. All right, sorry, xn and xn here. Get it put in my subscripts. Okay. Does that feel okay? Like, if the first part works, then the second part will work, right? And the truth is any of those root finding methods that worked before will also work here, right? All this requires is basically if you're given g of x, right? If you're given g of x, you have to just find the derivative of that, and then you just say, well, let's apply a root finding method to the derivative of the function that I want to optimize. That's kind of our first class of optimizers. Okay, so you have some function g of x. All right, so then find g prime of x and let that be f of x, and then just apply a root finding method here. Okay, and then so here we'll do pseudocode for Newton-Rapson optimization. I'm going to run out of time for my next thing. Can I skip the pseudocode? You want it? You want it? Okay. All right. Okay. All right. So we'll say g is going to be a function of x, and what should this function return? It should return three things. Okay. So we'll have gx being basically whatever the function is, and then it needs to return g prime. And you got to figure out the derivative, and then g double prime. I don't know why I wrote everything out, but okay. And that's going to be the second derivative, right? So this requires a little bit of math in that you got to find the derivative and you got to find the second derivative, right? Just throw your function at Wolfram alpha and say, what are these derivatives? Oh, I mean, really, if you're going to use Wolfram alpha, just say, what's the maximum? But yeah, okay. And then what it's going to return three values. It's going to return, we're going to just combine g of x, g prime, and g double prime. So you do that, and then you can, so you say g of 5, and then you can do bracket 3, and this will be the second derivative at g of 5. Okay, and then as far as the actual code goes, so Newton-Rapson will be a function, and we'll need to have three things in there. We're going to have g, we're going to have a starting value, x0, and a tolerance. And then what do? We say x old is xo, and then I guess we can create a while loop. So while the absolute value of x new minus x old is greater than the tolerance, what are we going to do? We're going to say we should do x old is we probably need to have an x new in here, okay? And x new we will update as x old minus, and you will do g of x old, the second value, which is going to be the first derivative, divided by g of x old, the third value that the function returns. And then you close off your while loop, return x new. Sorry, this is really messy. It works here. Yeah. Sorry, it's really messy. Basically, the same code that worked for Newton-Rapson for optimization will work here. All you have to do is you just have to change it so it's using the second derivative and the third derivative. You also have to rewrite your function g so that it returns three values, or really just two, being the first and second derivatives. Are there questions on this? And then, yeah, again, pretty much any of the root finding methods that have worked, if you can find the derivative, apply root finding method to a derivative, you'll find the critical points. Is that okay? All right. Okay. We've got the golden section search. Maybe I'll link you to a video on this. It's a good video. All right. Golden section search. All right. What's the, you guys know the golden ratio?
Yes.
Yeah, right? We love this thing, right? You get the nice little spirals. All right, what's the golden ratio? What's the property of the golden ratio? It's like, you know, 1.618, but what is the property? The idea is that you got some box, right? And then you add on a length of 1, and the ratio between 1 plus x over x is the same as the ratio between x over 1, right? And then you solve for this thing and you get like, you get 1.618. Okay, why are we going to do this? Well, the idea is that let's say you have some function here. And we will we'll bracket this off. Okay, and so here I'm going to put A and B, and we'll have some point C. Okay. This is like too close to the maximum. Even if C is like over here where it's clearly not the maximum, the thing holds here. And the idea is that if you've got some function where C is between A and B, or we would write A is less than C is less than B, okay? And if and f of A is less than f of C, and f of B is less than f of C, then there is a local max between A and B. Like, that has to be true. Okay? It doesn't necessarily have to be C, but it does mean that there has to be a local max between A and B. Okay? The same can be applied to a minimizing function, right? So if you have what's going on here? Then, you know, same idea applies here. Okay. Actually, we should so I will write the code or the algorithm for minimizing the function, and if you want to apply it to maximizing, all you do is multiply the function by -1, right? And if you find the minimum of the function multiplied by -1, you're going to find the maximum of the original function. Okay. So how does this work? Well, let's we'll start off. Okay, and so we're going to start off with A, and we're going to start off with B, and basically this is going to be B minus the golden ratio is 0.618 times A minus B, or B minus A. One plus or minus, right? So 1 plus 1.618 or 0.618. The ratio between 1 and 1.618 is the same as 0.618 and 1. So that's what's good, okay? And then over here we have A plus 0.618 times the span between B minus A. Okay. Just for simplicity, like, I'll just use 0. Like if A is 0 and 1, here I'm going to have basically 382 and 0.618. Okay. And what do we do? Well, we find f of a. I'm going to call this what should I call this? M1 and M2. Maybe the book uses different letters. Okay, we'll find all of these. And then, and this is not a good picture here because these two look like they're at the same level. The idea was that one of these is going to be obviously higher than the other. All right, let's just say the function goes up to there or something, right? And this line goes vertical. We calculate. We say, okay, we've got the function here, and we calculate between M1 and M2. We say one of these is bigger than the other, right? And if so if M2 is greater than M1, if f of M2 is greater than f of M1, then we know the local min has to be between A and M2. Okay, and we can throw away the interval from M2 to 1. We know it can't be over there. Okay, because we are in a situation where you've got 3 points, A, B, and C, and we know that C is between A and B, and if C is less than A and B, then the local minimum has to be between here and here. So so you go back to the if you think back to the previous slide, and we said if I should have done it the other way, but if C is in between A and B, then we know that there has to be a local minimum or a local maximum if the value there is there. And then so here we have a situation where, and I have run out of time. I'm having trouble here. And here we have a situation where we have basically 2 endpoints. We're just trying to find a set of 2 endpoints that we can guarantee there is a local minimum in between, right? And so if we pick this one and this one, because this one is below these two, we know there has to be a local minimum there, right? If I picked this one, and this one is larger than one of the 2 endpoints, it doesn't guarantee that there's a local minimum in between them. So what we've done is we've picked 2 middle points, and based on these we can be sure that there's a local minimum here. Okay, we're gonna have to end here, and we'll continue this on. Yes. It doesn't have to be between 0 and 1. It's A and B. Just for illustration, I was picking these numbers to make it a little easier.